So in this lecture we will continue to talk about large deviations. So it's a continuation of last class. We will start talking a little bit about properties of the rate function that are interesting on their own. And then we'll talk a bit about lower bounds and why the upper bounds we got in the last class are somehow optimal. So first, let's talk a bit about the rate function again. So before stating any proposition, let's recall we had a random variable x, or a measure mu, and x was distributed as mu. And we defined the Laplace transform of mu, or Laplace transform of x, at point theta as the expectation of e to the theta x, whenever this is finite. It's definitely well defined, because if it's infinite, we define this on 0 infinity. And then we defined the Legendre transform of the Laplace transform, which is the rate function. So at point x, this is just the supremum over theta of theta x minus the logarithm of the Laplace transform. And we had an interpretation for this that's going to become even more clear after the following proposition. So suppose that we have the setup above, then both, by the way, this is also on 0 infinity, then both the logarithm of L mu of theta and I mu of x are convex functions. And when I mean convex, you should understand what's the algebra of infinity. So for example, a function that is infinity until a certain point, then it's 0, then it's infinity again. This is a convex function, although it doesn't look, because when you do the convex combination between here and here, so you're taking eta times 0 plus 1 minus eta times infinity, this is infinity. So the convex combination is always infinity. So it's still a convex function. I'm not going to enter in detail of what a convex function like this is, but the definition is the same. We would like to have f of eta x plus 1 minus eta x, y, to be so smaller or equal than eta f of x plus 1 minus eta f of y. And in case anything here is infinite, and you multiply by a positive value, it's still infinite. If you sum with something, it's infinite. So in this context, it's clear what a convex function means. And these two functions are convex in this sense. So let's look at the proof. The proof is actually quite simple. So first we're going to deal with so when we say that the logarithm of a function is convex, sometimes people say it's log convex. So we fix a between 0 and 1. So instead of eta, we're going to use a here. And we look at not the logarithm still, we are going to put the logarithm later. For now, we're only going to look at this. So fix theta and theta prime and look at this. This is an expectation of e to the something times x, but exponential of the sum is the product of the expectation, so we can write this as such. Sorry, x. And here you see that we have exponents a and 1 minus a. It's very tempting to use Holder's inequality here to bound this by the expectation of e to the theta x to the a and expectation of theta prime x 1 minus a. So the fact that we have exactly 1 minus a here and a, and we are using p and p prime as duals in Holder's inequality gives us exactly this. So this is very convenient for proving convexity, because now this is just the Laplace transform of mu at theta to the a, the Laplace transform at theta prime to the 1 minus a, and after we take logarithms on both sides, we get here exactly what we are looking for, the log of the Laplace transform evaluated at this convex combination. And on the other hand, we have a times the log plus 1 minus a times the log. So we get the result. And by the way, here I'm saying that the convexity will hold even in the case something is infinite, and when one of these is infinite, this bound is trivial, everything becomes trivial. We are proving convexity, but just proving that something is smaller than infinity, smaller or equal than infinity. So this solves the case of the log of the Laplace transform. And now we're going to focus on the rate function I. So the rate function, if we recall its definition, at the point x is the supremum over theta of theta x minus log of L mu of theta. And what's interesting is that given theta, so if you fix theta, this function here is an affine function over x. So it could be, it doesn't matter what the log of the Laplace transform is. This is just a coefficient. This is another coefficient, and this is an affine function. So this is convex. Being an affine function, this is convex. And now the rate function is the supremum of several convex functions, and this is always convex. So supremum of convex is convex. So this shows the result, even in the case that the supremum can attain infinite at some point. That doesn't change this claim. And moreover, this shows that I is lower semi-continuous, which is also nice. The supremum of lower semi-continuous functions like this, like affine functions, is also lower semi-continuous. So this is another nice result about the rate function. So now that we know both are convex, we can have a better picture of what this is doing. So we have the Laplace transform here. We know that it's 1 at 0, and then it's convex, and it's non-negative. Could do something like this though. And we're going to take the logarithm of this, which is still convex. We proved that the log is convex. Now the logarithm hits 0 at 0, and it could go negative. So this is, oh god. This is the log, for example. And we take minus this, so this is log of L mu. Then we take minus this, and we take the Lagrange transform, which is just taking this is not very nice, but this is the idea. For every angle x, so this is x times theta as a function of x, you take the point where this hits here, and this is I, mu of x. So this is the definition of I, and it's also a convex function. One interesting observation is that when you take x equals 0, you're taking the flat function. It's not affine anymore, it's constant. So this supremum here, the I mu of 0, is the supremum of minus log of L mu of theta, supremum over theta. So another way to say this is to say that minus I mu of 0 is the infimum of the log of L mu of theta. Sorry. Yeah. So this is the first property that we are proving, the convexity. And now we are gonna show a little bit more about what this rate function looks like in the next proposition. So suppose that the L mu of theta is finite for all theta in some interval minus epsilon plus epsilon. So in some neighborhood of the origin, the Laplace transform is finite. I will talk a bit more about what this hypothesis implies, but then we know that I mu of x is equal to 0 if and only if x is the expectation of mu, sorry, the expectation of x. So just before we prove, we know that the rate function gives the rate of decay, and what this theorem is saying, this proposition is saying, is that, you know, if we have this finite Laplace transform, which is always a hypothesis when we're doing this type of things, we want the exponential tails for mu, then the only place where there is no exponential decay is around m. If you want the variable to be here, it's going to have an exponential decay. If you want it to be here, there will be an exponential decay. Because the only place where the rate function is 0 is at the mean. So first let's observe that the hypothesis that the Laplace transform is finite for every theta in minus epsilon epsilon is a very strong moment condition on mu. It's saying that e to the epsilon, say epsilon prime, x has finite expectation, so x cannot have a very fat tail to the right. It's the tail to the right has an exponential moment. So the fact that this is finite says that the expectation of x plus is finite. And the fact that this holds with a negative epsilon prime says that the negative part also has exponential finite expectation. So the tail is also light to the left. So in essence, this is a well-defined quantity. Okay, we're not talking about infinite when we take the expectation of x. Now, we saw before what happens when we take a random variable x and transform it to y, which is ax plus b. We saw that the Laplace transform of x is also transformed into the Laplace transform of y. Sorry, here should be theta. Which is just the Laplace transform of x evaluated at x minus b over a theta. So we saw how these linear transformations, affine transformations of a random variable, if a is different from 0, give you a way to transform the Laplace transform. So in essence, let's go back here and observe that if you subtract a constant m from x, we still don't change this by adding a constant. And now the fact that the rate function is 0 if and only if the x is m is going to translate to the 0 point now. So it's not difficult to see that we can assume without laws of generality that m equals 0. So all the transformations also translates to I, and you get this equivalence also after subtracting the expectation. So let us recall what we know about the Laplace transform. We call this sometimes the moment generating function because the derivative of this is the expectation of x e to the theta x. So when we evaluate the derivative at 0, we get the expectation of x. So that's why it's called the moment generating function, because if you take other derivatives, you're going to get other moments. But one important point is that this is now known to be 0. So the derivative of this function is 0. Let's look at the logarithm. If we take the logarithm of the Laplace transform, differentiate, we're going to get 1 over the Laplace transform times the derivative of the Laplace transform. So it means that the derivative of the log at 0 is also 0, because the numerator is going to vanish here, and the denominator is always positive, right? This function is always bigger than 0. So we've got our result on the derivative. So when we recall what this function looks like, especially the minus log, so let's draw here minus log of L mu of theta. We know that this is now a concave function. Minus something that's convex becomes concave. Its value at 0 is 0 because L mu of 0 is 1. Sorry. So the log is 0. So its value is 0. It's concave, and the derivative at 0 is 0. So this function is non-positive. Why? Imagine that you had some point where the function was strictly positive. Then this would be a lower bound on the function by concavity. So we would have a derivative which is not 0 here. So this function is smaller or equal to 0. What this implies on the I side, so I mu of x, I mu of 0, I want to calculate I at 0, which is the mean of the random variable x. This is the supremum of 0 times x, which I'm not going to write, of the above function. And we know that this function has value 0 here, and it's smaller or equal to 0 everywhere, so the supremum is exactly 0. So we just proved that I of 0 is 0. Actually, we proved that I mu of m is 0. By this linear transformation, we proved it for 0 when the expectation is 0, but in general, if the expectation of x is m, I mu of m is equal to 0. Now what we have to show is that this is the only place where the rate function is 0. And the way we are going to do this is, forgetting that we are assuming now expectation of x to be 0, let's now assume the opposite. The expectation of x is negative. So here is 0, and here is the expectation of x. And we can do a similar argument for m positive, so I'm not going to do this. I'm just going to consider this case. And I'm going to show that the rate function I mu of 0 is negative. Sorry, I mu of 0 is positive. So here we have a positive rate function. And since we took a general case of m here, you know that shifting m only shifts the rate function. So this is a general case. If we show that the rate function at 0 is positive, we are done. Because whenever you have some m anywhere and some point to the right, you can shift everything so that this point x becomes 0, the new 0. Okay, so this is what we have to prove, that the rate function at 0 is positive. So what is the... Let's show that the minus rate function at 0 is negative. So this, as we saw, at 0 is the infimum over theta of log of the Laplace transform. Now let's look at this logarithm here. At theta equals 0, this is 0 because the Laplace transform is 1. And the derivative at 0 is the expectation, sorry, it's the derivative of the Laplace transform at 0 over the Laplace transform at 0. So this is the derivative of the log, and the denominator is positive. Actually, the denominator is 1. And the numerator is the expectation of x, which is m, which is negative. So this function here that we're trying to take the infimum, we know that it's convex. Its value is 0 at 0 here. And its derivative at 0 is negative. It's going there. It's convex. So the infimum of this is negative. So this is negative. So I mu of 0 is positive. So yeah, not a big proof, but it involves understanding, you know, how to translate the fact that L is the moment generating function into these Legendre transforms, which are a bit annoying but not complex. Okay, so we now have some good vision of what our functions look like. They're convex. The rate function is 0 only at 0. And now we are going to recall what we proved in the last class to connect to what we're going to prove now. So in the last class, so let us simplify our lives and suppose for now on that the Laplace transform at theta is finite for every theta. So this is not necessary at all. And if you're doing large deviations the right way, you shouldn't lift this condition. I mean, you should only need theta, this to be finite in some interval, and then you work on that, some interval around 0. But we're going to simplify our lives. So suppose that the Laplace transform is always finite, then you don't have to treat cases of infinite Laplace transforms. And in the last class, we saw a theorem that took a sequence of random variables, which were IID with distribution mu. Sn was just the sum of xi, and we proved that the probability that Sn over n is bigger than x as soon as x is larger than the expectation, which we call m. The probability that the average is larger than x, larger or equal, is smaller or equal than e to the minus I mu of x. So this was a very nice theorem, but a simple consequence of the exponential Markov inequality. Now, as I said, this is an upper bound, and we're not going to look now for lower bounds. Of course, an important observation, sorry, this is not theta. An important observation is that we cannot hope to prove the exact, I mean, you're going to get sharp lower bounds, but we cannot expect this, right? This is too much, because then it would be an equality, and we don't expect the decay to be exactly this. Oh, by the way, I forgot an n here. So since we cannot hope for such a good decay, such a good low bound, what do we expect indeed? So let us look at the graph again. We have a graph, we have here the average m, and the rate function is not 0, it's only 0 at m, after it grows to both directions. So here we have, for example, a value x which is larger than m. By the way, a similar statement holds for x smaller than m. And we're saying that the measure of this whole half line here is exponentially decaying. Actually, if something happens in this line, if the Sn over n is in this half line, where do you expect it to be? I would expect it to be very close to the limit here, because being here has a e to the minus I mu of x probability, but being here at a bigger x prime has an even smaller probability, e to the minus I mu of x prime, which is much, much smaller. By the way, I always forget n. So I expect the variable to be close to the limit of the interval. If you want it to be larger or equal to x, it's going to be pretty close to x. What the next result is going to estimate is the probability that Sn over n belongs to x plus minus epsilon. So this is actually going to call it delta, but you got it. So this is what we're going to estimate from below. So this is very related to the upper bound given there, but we, as I said, cannot expect to have a matching lower bound. And another observation is that this is not asymptotic. It's something that holds for every x, every n, every variable mu. This is a statement that is a finite statement. In the next theorem, however, we're going to give an asymptotic estimate. So this is the important theorem of the class. This is Cramer part 2. There are several different ways to state this, but I'm not going to enter into these details. Let's assume two things. They are not big assumptions. They are not present in the original theorem. They are just to make our life easy. So assumptions, first we assume that the Laplace transform is finite for every theta. This makes our life easier. And second, we assume that so we're gonna take x in R, and we assume that the probability to be below x, and the probability to be above x are both positive. This is very technical, it's not necessary, but we want to make our life easier. We're not gonna use this theorem with sharp assumptions to this class. This class is to give a very strong argument that the upper bounds we obtained are sharp. Okay, so what does the theorem state? Is that the limit in n of 1 over n log of the probability that Sn over n is larger, so x, sorry, not larger, is in x minus delta x plus delta is equal to minus I mu of x. So before going to the proof, let's look at why this is a lower bound of the type we want. So I promised the lower bound, so let's see why. So you remember that the probability that Sn of over n belonging to some, x minus delta x plus delta, at least for x bigger than m, we knew that this was smaller or equal than e to the minus I mu of x minus delta. Right, this was n. This is what we obtained from the upper bound. Of course, we can take logarithms on both sides. It's a monotone function. So the log of this probability is smaller or equal than minus I mu x minus delta n. Then we can divide by n on both sides. And we can take the lim inf, and we're going to get that the lim inf in n of 1 over n log of the probability is smaller or equal than I minus I mu of x minus delta. And here we're getting an equality. That's why I'm saying it's a matching, sorry, it's bigger or equal. So that's why I'm saying it's a matching lower bound. But important to notice, this is indeed an asymptotic statement. So this is not for fixed n and fixed delta. It's you're given a delta, and for n large enough you know something, but you don't know how large. You have to take n to have the lower bound. But on the bright side, this gives us no hope to improve what we already had in the first part of Chernoff. Okay, so the proof is not going to be very long, but it's a very ingenious proof. It's a beautiful proof that applies in several other contexts where you're trying to show exponential lower bounds of this type. So whenever you have some event that you know decays exponentially, and you want to show that it decays not too fast, you want to show lower bound on the exponential decay of your event. And I repeat, this is extremely important in statistical mechanics. This technique is a golden one. It's very useful, it's very powerful, and it's called change of measures. So the idea behind this proof is the following. I don't know how this decays. I know that if the expectation of x was equal to little x, then the probability that we are talking about would go to 1. So this is a good lower bound. It goes to 1. But I don't know if this is the case. Maybe it's not. I mean, the theorem is much more interesting when this is not, because when this is the case, this is going to be 0, and you got nothing. So if x, the expectation of x is not this, which is usually not the case, we change x to y, we change the measure mu to some new, and change the variable x to y, such that the expectation of y is indeed x. So you now have the lower bound, and you have to calculate what's the cost of pretending that you had a different measure. So this probability is going to be lower bounded by the cost to change measures. And this is going to be exactly this. So this is what's the magic of this proof, because we're going to use a change of measure that is very specific. It's exponential. I'm going to explain this in the proof, but this is the idea. And let's start with the proof itself. So as usual, without loss of generality, we can assume that m is 0 and x is different from 0. Let's assume x is, oh sorry, we're going to assume that x is 0, sorry. And we know that mu of minus infinity x is positive, as well as mu of 0 infinity. So in particular, you see, what does this mean? It means that if you plot the distribution of mu, it has some mass here and some mass here. So when you look at the Laplace transform of mu, as soon as there is some mass here, when you take e to a very large constant times x, this is going to diverge. So this is going to infinity as theta goes to plus or minus infinity. So the plot of the Laplace transform is going to blow up. Oops, starts at 1. It's going to blow up like this. Okay, so this is going to be useful, because if this goes to infinity, the same holds for the log. So we can, since the log is convex, I'm going to use the same picture here. So this could be a picture of the log of L mu of theta. And this means that minus log of L mu of theta has a maximum, an overall maximum, a concave function that goes to minus infinity on both directions, minus and plus infinity. It has an absolute maximum. So there exists a theta 0 such that minus log of L mu of theta 0 is bigger or equal than minus log, or the supremum over theta of minus log of L mu of theta 0. Which, by the way, if you remember, this is I mu of 0. So you see, we are assuming that 0 is the point that we want to find the deviation. So here is x. Mu doesn't need to be, the average doesn't need to be x, the mean. So we have a picture like this. And the value here, I mu of 0, that should give you the exponential decay, is minus log of the Laplace transform at some point theta 0. Okay, so let's plot here the minus log L mu of theta 0. So x here is 0, and we're getting a positive thing. So, and m is negative, so the derivative is negative, and this is minus, so the derivative is positive. We get something like this. So this is a good plot of log of L mu of theta, and this is theta 0. Okay, so this step, you see, we made strong use of this artificial assumption that things go to infinity. If this is not the case, you can still analyze. What's going to happen is there will be some cases where theta 0 is going to be essentially minus infinity or plus infinity, or you still never attain the maximum. There will be no point that attains the maximum, but you know where it's going. You have to make an analysis of several different cases, and we don't want to do this here. But the spirit of the proof is it doesn't change at all. Now let's again use the definition of the fact that this is a moment generating function. So when we take the derivative of this and evaluate at theta, what we get is the derivative of what's inside over what's inside. And we know the derivative of the moment generating function is the expectation of x e to the theta x. So let us evaluate this at theta 0, right? So if we put a 0 here, this is of course still true. And the interesting thing is that since this is a maximum of a convex function, the derivative is 0 at the maximum. No, it's the maximum. So if it's differentiable, and it is, the derivative is 0. This denominator here is positive. It's expectation of a positive function. So we know the expectation of x e to the theta 0 x is 0. And why is this interesting? So let us understand what is going on here, and this is going to be essentially give us the change of measure that we need to do. All we have to do is understand this. What we are saying, somehow we would like, so between quotation marks, we would like to say this is the expectation of some variable y that is 0. So the expectation of y is 0. So y is gonna be around, so if we change the variable x to some variable y, the sum is gonna be close to 0 with very high probability, because we are now making the sum of variables that have 0 expectation. So the average as n over n is going to concentrate around 0. So this is the spirit. We want to replace x by some y. And this should be the expectation of y. This is all we want. So let's write this expectation in an integral form. This is the integral of x e to the theta 0 little x mu of dx, right? Didn't do anything here. We know this is 0. And this looks very much like a Hadon-Nikodym derivative. So in our intuition mode, we would like to say that we are changing the measure mu to some measure nu, and d mu is going to be e to the theta 0 x. But now this is very dangerous, because I don't know if this is still a probability measure. If we just multiply some measure by some exponential, if you use this exponential as a Hadon-Nikodym derivative, I don't know if this is still a probability measure. But I can try to normalize. So this is definitely a positive and finite measure, because we are assuming exponential moments to be finite. So remember that we are assuming this. So the nu that we defined underneath here is a finite and positive measure. That's fine. But we don't know if it's a probability. How do we know if it's a probability? We have to integrate nu. So this is the integral of our attempt of nu and see what happens. So let's copy this to the next page. So what is this? This we can rewrite again as expectations. We prefer expectations as probabilists. This is the expectation of e to the theta 0 x, which is the Laplace transform at theta 0. This is a nice number. And this is not necessarily 1, right? We know that the Laplace transform at 0 is 1, but at theta 0 I have no idea. It's actually larger than 1, right? Because, sorry, smaller than 1. Because the minus log is bigger than 0. So we have this, and we would like to have mu to be a probability. So to make this into a probability, we're going to divide by this. Then we are sure that it integrates up to 1. This is theta 0. So now we have, if we started with like nu of the real line is equal to the integral on the real line, but now the definition of nu has this, and we'd get here we would have 1. So nu becomes a probability if we do this right normalization. And now, as promised, we say that y1, y2, and so on are IID random variables. They're all distributed as nu. And what's the expectation of y? This is the integral of y nu of dy, which is the integral of y e to the, sorry, there is 1 over something here, e to the theta 0 y mu of dy, which is the expectation of x e to the theta 0 x over something, which is 0. So y has 0 expectation. Also, if you look at the definition of y, it's just a Hadonic-Odin derivative of x. What we get is that y also has all the Laplace. The transform is always finite. We're just multiplying by some e to the theta 0 y, e to the theta 0 x. If they were all finite before, they're all finite now. This is another point where the assumption that everything is finite here is helping us a lot. So we are assuming this. This is helping now, but it's a technical help. We could survive without this assumption again. We just have to understand what is the interval where this is finite, and this interval is going to contain the origin, and we're going to be happy. So it's a technical issue, but it can be solved. So now we are very close to finishing. If we define Rn just like we defined Sn before, it's the sum of yi now, then we know that the probability that Rn over n belongs to minus delta delta goes to 1, because this implies that the expectation of y is finite. It's actually 0. So by the weak law of large numbers, we have convergence to 1 and have this lower bound here. So now we have to just see what the price is to replace S by R. So originally we wanted to bound this. The probability that Sn over n belongs to minus delta delta, not R, S. Okay, so let's fix theta prime smaller than theta. Sorry, delta prime smaller than delta bigger than 0. And this, of course, we can replace by delta prime. There is nothing here. If it's inside minus delta prime, it's also inside delta minus delta delta. So we didn't do anything here. Now let's write this in the integral form. I know probabilists don't like the integral form, but sometimes it's useful to visualize things. So we are integrating over all little xi's. So we have variables little xi, such that if we sum this for I equals 0 to n minus 1 and divide by n, this is smaller than delta prime. So this is the region we are integrating, and the measure we are integrating is mu times mu times mu, etc. So it's just an integral in this n-dimensional space with this product measure, but we are integrating a special diagonal set here. Things that sum up to something smaller than delta. It's a band somehow. It's like a hyper space band. So now the advantage of writing it like this is that we can really replace mu by nu and pay the Hadonic-Odin derivative. So what's the Hadonic-Odin derivative? So first there will be lots of L mu of theta 0. That was the normalizing constant. This will appear n times. Now we are integrating on the same space, same set. This is just a set. We are still integrating here, but now we're going to replace everything by nu. And we still have to multiply by here the Hadonic-Odin derivative. This is e to the theta minus theta 0 x1, e to the minus theta 0 x2, but the product of exponentials becomes the exponential of the sum. I from 0 to n minus 1 of xi. So you see, we got, this is just equality because we are replacing, we are just using the fact that what is here is the Hadonic-Odin derivative of mu with respect to nu, the opposite of what we did before. And since they are positive Hadonic-Odin derivatives, we can invert this. So this is an equality. And now what's very convenient is that the set that we are using to integrate here is appearing here very conveniently. So we can lower bound this by, again, this factor. Who cares about this factor, right? It shouldn't be important unless it is. And now I'm going to remove this by something that's definitely smaller than this. No matter what point we are inside the integration set, it's going to be a lower bound. So the lower bound is e to the minus delta prime theta 0. Because this sum, even in absolute value, is more or equal than delta prime. So if we replace this by minus delta prime, we get, oh, by the way, there's an n here. I can, for example, write it like this. So there is an n here, because here there was no 1 over n. Here I can write it like this. So now this exponential is always larger than the minimum value we can have, which is e to the minus delta prime n times theta 0. And now we have the integral blah blah blah, and this integral of nu is exactly the probability that r n over n is between minus delta prime and delta prime. Okay, so now we are almost done. We have a lower bound for our probabilities. I'm going to copy the lower bound below. And we're going to take the log of this and divide by n. That's what we are looking for in our final estimate. So this will be, the n will go down in the log, and we're going to divide by n here, so it's going to disappear. So the lower bound is going to be log of L mu of theta 0. Then we're going to get a log of this, so minus delta prime theta 0. You see the products become sums. The minus sign, the theta 0 and the delta prime go down. Then the log of e to the n is n, and divide by n disappears. And finally we have plus 1 over n log of some probability. I don't care. It is what it is. Again, I need to go to the next page. I know there is a way to make an infinite page, but I'll try to find out next class. So this is what we've got until now. So observe that this goes to 1. So this goes to 0. So if you divide by n, it goes even faster to 0. So this is not what we have to care about. When you take the limit, this disappears. If we take the lim inf in n of 1 over n log of this probability, we are going to get a lower bound of the type log of L mu of theta 0 minus delta prime theta 0. And this is true for every delta prime in 0 delta. So in particular, this is also true. Now what is log of L mu of theta 0? I said this normalizing constant, nobody should care about it. Actually, it's exactly what you should care about. The log minus log of L mu of theta 0 is I mu of 0. So this is giving us minus I mu of 0, which is exactly what we wanted. So in essence, the price we pay to change the measure for something that would have been a large deviation, so this is a large deviation, be close to 0, be close to x where x is not your expectation, this is a large deviation. But replacing the measure to some other measure where this is not a large deviation anymore, this is something very normal, is costly, it's exponentially costly, and if you choose correctly the way to change the measure, the cost is this. It's exactly the normalizing constant to the n. And the normalizing constant happens to be the rate function. So this finished the proof. I hope you enjoyed this proof. As I said, is very elegant and applies to different contexts. You want something to lower bound the probability of something very bizarre, you change the measure. Now that bizarre thing is not bizarre at all. There's a law of large numbers saying this is going to happen with probability going to 1. And instead of now trying to estimate the probability of something very small, you're just estimating the price you have to pay to change the measure. This is a very powerful and general idea. Thank you. See you next time.